Hello and welcome to this video on working with applications of functions. So in this video I'm going to go over just one example I've pulled from an intermediate algebra text in which we deal with a function that relates to a real-world problem. Right? We'll be asked some questions about that function and about that particular problem. All right, so let's get into it. So here's the problem I pulled. So we see in 2010, the Deepwater Horizon oil explosion spilled millions of gallons of oil in the Gulf of Mexico. The oil slick takes the shape of a circle. Suppose that the area, denoted by capital A, for area, suppose that the area in square miles, the units of the area, suppose that the area A of the circle contaminated with oil can be determined using the following function, where A of t, or the value of A at t, equals 0.25 or 1/4 times pi, right? That's the 3.14159, that's the number pi, times the variable t squared, right? Where t represents the number of days since the rig exploded. Alright, so got a word problem here, a little real-world application. This is a particularly nice one. In future videos we'll see word problems and stuff where we'll have to write our own function describing the situation. Here in this particular one I'm just showing you a nice one where a function is given to us. This one here describing the growth of this oil slick. Alright, so this oil rig explodes, and then oil contaminates water, and it's in a circular shape, and that circle keeps getting larger and larger as the days go on, as more oil spills into the water. Alright, and I'll draw a little diagram, a little picture to go along with this in a second. Alright, so first we're asked, part A is to identify the dependent and independent variables for this particular problem. All right. So in previous videos I've talked about functions. Again, if you've been watching them, fine. If not, you can go back and look at them if you want. But when we've seen functions written out in function notation, for example, f of x equals x squared plus 1 or something, right? This is just a separate example. The notation tells us what the input is and what the output is. The variable in parentheses, the x in this case, is the independent variable or the input of the function. It's a value from the domain of the function, however you want to say that. But that's the independent variable. And then the other, the name of the function is sometimes referred to as the output. Right, so f or f of x, right, the whole thing, is referred to as the dependent variable, or the value of f at x is, and then over here on this side is an expression describing how this variable from the domain corresponds to a variable from the range, how this input corresponds to an output, how you need to calculate an output. Square the input, then add 1. So sometimes it's just the name of the function or the actual whole thing, f of x itself, is referred to as the dependent variable, right? It's almost like the y coordinate, right? The output, if you're talking about x and y coordinates on the xy plane. Right. So for this particular problem I was reading about the Deepwater Horizon oil explosion, the function we are given, I'll write it again down here so we can point some stuff out, is the value of a at t, right, or a of t if you want to say it that way, is equal to 1/4, right, 0.25 times pi times the value of t squared, right? So the variable t in this case, right, again, the expression in parentheses here, what's being plugged in, what's my input? T, right, the time, right, this number of days since the explosion. This is the independent variable. All right, my inputs. And then the name of the function, right, this is the function a, and a represented area, right, that was mentioned in the problem, right? Suppose that the area A in square miles of the circle contaminated with oil, right? So the name of the function a, or again you can say a of t, but let's say a, the area of the circular oil slick. This is the dependent variable, right, the outputs. Alright, so that's the answer to part A, right? It's based on the way the function looks, the way the equation looks. It's very easy to determine what's my inputs, what's my outputs, independent variable, dependent variable. T, time, independent, A, area, dependent. Okay. Now let's take a look at what's happening here, right? I'm gonna draw a little diagram on my next page before we get into part B. All right, so what is actually happening in this particular problem? All right, so let's suppose that this blank piece of paper I have here now is the Gulf of Mexico. All right. So suppose this blank sheet is the Gulf of Mexico, and I'll say this dot here is the oil rig. Alright, and then this explodes and a bunch of oil starts seeping into the Gulf of Mexico. A bunch of oil starts contaminating the water. Well, it's going to contaminate the water modeled by this equation, right? And I said, suppose the oil slick forms a circle. Well, when it first explodes, there's not much. It's just right around this point. I'll do it in black here. That's the oil. When it first explodes, there is really no circle to speak of yet. So that would be when t equals 1, right? Remember, this is time and days. So, or I'm sorry, t equals 0 when it first explodes, right? 0 days in, right when it first explodes, the oil is contained to just the rig. But then 1 day later, right, I'm going to punch this into a calculator, but when I replace t with 1, the area at 1, I'll write this off to the side, the area of the oil slick when I replace t with 1, a of 1 here, would be 0.25 times pi times 1 squared, right, replacing t with 1. And again, I'm going to punch this in a calculator and round it. It's 0.25 times pi, and then 1 squared is just 1. So this is approximately 0.785. And don't forget, this is square miles, the area of this circle. Square miles, it's an area. So after 1 day, each day the circle is going to get bigger, right? So after 1 day, the oil has expanded out, more and more oil has poured in. Again, it's not, I'm sure in real life it wasn't a perfect circle, So let's say the oil starts expanding out, pouring out, and creating this circle, this bigger circle, and say that's when when t equals 1 day. 1 day later, the oils expand out this far, covering an area of 0.785 square miles, and then it just keeps going. After 2 days, what's the area? I'm just going to replace t with 2. This is 2 days later, and just following the model, replacing t with 2. The area after 2 days be 0.25 times pi times 2 squared, which is 4. So this is just pi, right? Because this is a quarter. A quarter times 4 is 1, and then times pi would just be pi. So it's approximately 3.142, because it's 1415, round up to 142 square miles. Right. So again, what's going to happen is 0 days it's at the rig, explodes. A day later, the oil slick is bigger, and then another day later, the oil slick circle is even larger. Right, so another day later, it's expanded out even further, poured out even further. There's more and more oil going into the ocean, and there's when t equals 2. And hopefully you can see what's happening in my picture. It's not very dynamic. I mean, it's not moving, but hopefully you can see it moving, feel it moving in your mind. Right, it starts off at the rig and then just keeps expanding, larger and larger circles the more and more time goes on. All right, so that's a picture, a little diagram of what's happening in this problem, where the area of the oil slick is modeled by this equation, this function. Okay, so working on now to part B. After 1 day it covers 0.785 square miles. After 2 days it's covering an area, a total area of pi square miles. Well, part B is asking what's evaluate, find the value of, that's all evaluate means, find the value of A at 30 and explain what that means. Right, so let me do that down here. A of 30, right, the value of A at 30, and you go to your function A, this guy up here, and replacing the input t with 30 throughout the rule, is 0.25 times pi times 30 squared. All right, and that's 930 squared. So 900 times a quarter times pi, and I'm going to approximate that. I'm going to round to 3 decimal places, the nearest thousandth, like I did with the previous examples. So 0.25 times pi times, and then 30 squared, or 900, and I get approximately 706.858 square miles for the area that this oil slick is covering after 30 days. And I'll write what this means in a second. Well, I said what it meant, but again, thinking about this picture up here, day 0 when it first explodes is nowhere, but it's still at the rig, and then a day later oil slick's larger, a day later the oil slick's larger, and then we just keep thinking out to 30 days after the rig explodes. The oil slick, if the oil is not contained, if it's not stopped, the oil slick's just going to get larger and larger and larger and become this larger and larger circle. And here's when t equals 30. 30 days later, the oil slick's taken up a little over 700 square miles of the Gulf of Mexico on the surface, right? So that's what that means, right? That's what this A of t means. It's just the area of the oil slick after t days, right? T days after the explosion. So A of 30 simply means the area of the oil slick (30 days) after the rig explosion. And that's all it means. And there's nothing really more to say about that, because that's exactly what those variables represent. 30 represents T, which is time after the explosion, days after the explosion, and A is simply exactly what I said, the area of this circular oil slick, area of contaminated water around the rig. Okay, great. And that's really all you have to read into things. When you're given a function, like my one back here, f of x equals x squared plus 1, or this, a of t equals 0.25 pi t squared. So remember the input is your independent variable, the variable in the parentheses after the name of the function, and usually the name of the function is representing the dependent variable, the little f, the capital A. And yeah, and just remember what you're doing on the other side is simply calculating an output. What is the value of this function at x? It's this, and this over here is how I calculate that. What is the area after t days, t days after the explosion, and this is how I calculate that area over here. All right, so that's working with some functions, and in a word problem where we were given a function. As I said before, there's a lot of problems out there where you have to write your own, but we'll get into that kind of a problem at a future date. Alright, and as I like to say at the end of these, try your best, do the best you can to pick this stuff up, understand the material on your own before you go looking for help. Read the material, of course, read through the author's examples, perhaps even try to work out solutions to an example before you see how the author did it and compare, so see if you can learn from your mistakes there. Practice problems, practice exercises, look up solutions when they're available to check yourself. And just don't give up after the first or second attempt. Don't be so easily frustrated. Keep at it. If after several attempts at a problem it's still not clicking, you're still not getting it, then I would suggest that you read the material again, perhaps a little more slowly, a little more carefully, maybe even a third time. Because who knows, maybe on that second or third read through you'll see something that you didn't see the first time, or something will click that didn't click the first time through, and it'll make the problems that much easier to work on. But if after several attempts at a problem and several read-throughs of the material, it's still not working out for you, then it is not a sign of weakness whatsoever to go looking for help. Ask people for help. That is what people are there for. Ask a teacher, a tutor, a friend, someone else in the class who knows the material and is willing to help. Find supplemental materials online. There is plenty out there. Trust me, you'll find what you need to be looking for. Look for videos on the subject, perhaps like this one, or plenty of other ones out there better than this one. I assure you, you can find them. But just keep at it. Stay persistent. And try to stay positive as well. That makes a huge difference a lot of times. I know it's not very easy. If you've hated math your whole life and you've never been good at it, you're going to go in with that mindset every single time, and it's going to be a painful experience for you. If you just try a little bit, maybe do a little deep breathing beforehand, and play some soothing music, and think to yourself, go in with an open mind and think, I might enjoy this, I could take something from this, I'm gonna get through it, and I'm gonna have fun with it this time. Just going in with a positive attitude can make a huge difference. So just stay persistent, keep practicing, don't give up, have a positive attitude, and I just know you're gonna get it. All right, I know you'll eventually get it. All right. And thank you for watching.